In this paper, the concept of interpretable image enhancement is explored, which enhances image quality by adjusting filter parameters with easily understandable names such as exposure, contrast, and saturation. Unlike predefined image editing filters, the proposed method utilizes learnable filters optimized for predicting target enhancement results, allowing for high-quality enhancement. The paper introduces a novel filter architecture called an Image Adaptive Neural Implicit Lookup Table, IANILUT, which uses a multilayer perceptron to implicitly define the transformation from input feature space to output color space. This approach enables highly expressive filter effects and interpretable image enhancement. The proposed method also introduces a prompt guidance loss to assign interpretable names to each filter, utilizing CLIP, a vision and language model capable of embedding images and text within the same feature space. The prompt guidance loss ensures that when the parameter associated with exposure is altered, only the exposure score changes, while the scores for other impressions remain unaffected. By minimizing this prompt guidance loss in conjunction with a reconstruction loss of the target results, high-performing and interpretable filters are achieved. The proposed method is evaluated using the 5K and PPR10K datasets, demonstrating that the proposed method achieves interpretable filters that are understandable to humans and outperforms existing predefined filter-based methods. The proposed method, Prompt-Guided Image Adaptive Neural Implicit Lookup Tables, IANILUT, enhances image quality by introducing a novel filter architecture and a prompt guidance loss. The IANILUT filter architecture employs an implicit neural representation, allowing for highly expressive filter effects. LUT bypassing is used to expedite the transformation process. The prompt guidance loss assigns interpretable names to each filter by leveraging CLIP to evaluate the image's impression against guiding prompts. This approach addresses the limitations of existing methods by providing a framework that is both highly expressive and interpretable. The method's effectiveness is demonstrated through its ability to enhance images while maintaining the desired effects, such as exposure, contrast, and saturation, without confusing the user. The paper introduces a novel approach to image enhancement, utilizing prompt-guided image adaptive neural implicit lookup tables, IANILUT, for real-time and interpretable image enhancement. This method allows for the creation of filters that can be named and controlled based on guiding prompts, such as exposure, contrast, saturation, color temperature, and tint correction. The IANILUT is trained using a three-stage process, including the training of filters, image adaptive parameters, and a parameter predictor. The guiding prompts play a crucial role in achieving interpretable filter effects, as demonstrated in Figure 4, where varying certain parameters while holding others constant at zero results in specific enhancements associated with the corresponding prompts. To validate the effectiveness of the IANILUT, ablation studies are conducted. These include comparisons with 3D-LUTs, which show that the IANILUT achieves higher performance and better interpretable filter effects, Table 2, Figure 6. The LUT bypassing technique is also evaluated, demonstrating reduced computational costs without compromising PSNR, Table 3, Figure 7. Furthermore, the significance of the prompt guidance loss is assessed, revealing that it is essential for assigning interpretable names to each filter, Figure 8. The proposed method is tested on two widely used datasets, 5K and PPR10K. The results indicate that the IANILUT can achieve fast transformations with minimal computational overhead, making it suitable for real-time image enhancement. Additionally, the sequential application of predicted parameters is visualized in Figure 5, showcasing the enhancement process in an easily understandable manner. Overall, the IANILUT provides a novel solution for image enhancement, offering both efficiency and interpretability. This paper introduces a novel approach to image enhancement through the use of an interpretable and highly expressive filter architecture, named IANILUT. The proposed method utilizes a prompt guidance loss function to assign interpretable names to each filter, enhancing the understanding and usability of the image enhancement process. The authors compare their method with both interpretable and uninterpretable state-of-the-art methods, demonstrating its potential to bridge the gap between interpretability and high performance. The IANILUT filter architecture is designed to be highly flexible, allowing for various filter effects based on different guiding prompts. This is demonstrated in Figure 10, which showcases various filter effects achieved by assigning different guiding prompts to the filter. The authors also emphasize the importance of the prompt guidance loss in assigning meaningful names to each filter, as seen in Table 2. Without this loss, the filters may not be easily understood or controlled by users. Quantitative comparisons are provided in Table 4, comparing the performance of the IANILUT with other interpretable and uninterpretable methods on the 5K and PPR10K datasets. The results show that the IANILUT achieves competitive performance to uninterpretable methods while maintaining interpretability. However, a potential limitation of the IANILUT is the slight deterioration in performance when using the prompt guidance loss, as shown in Table 5. This could be addressed by refining the selection of guiding prompts in future research. The paper concludes by highlighting the potential of the IANILUT for enhancing image quality while providing interpretability. The development of an automatic prompt selection mechanism is identified as a future research direction to improve both interpretability and performance. The research paper discusses a novel approach to image enhancement using prompt-guided image adaptive neural implicit lookup tables, IANILUT. This method leverages the power of neural networks to adaptively generate lookup tables for image enhancement. The IANILUT includes an MLP for each filter, allowing for more precise control over the enhancement process. The paper highlights the importance of using sorted RGB values and the significance of the prompt guidance loss in achieving desired effects. An ablation study is presented to demonstrate the effectiveness of these components. The method is compared to other predefined filter-based methods and 3D-LUTs, showing a slightly higher number of network parameters due to the inclusion of the MLP. The paper also includes additional visualizations of filter effects and an analysis of the network parameters, further emphasizing the innovation and efficiency of the IANILUT approach. Here is the combined summary. The authors propose a prompt-guided image adaptive neural implicit lookup table approach for interpretable image enhancement. This method enables flexible and controllable image enhancement by learning a set of filter effects that can be composed to achieve desired visual outcomes. The approach is based on a neural implicit representation, which allows for efficient and flexible image manipulation. The filter effects are parameterized by a set of controllable attributes, including exposure, contrast, saturation, color temperature, and tint correction. By varying these parameters, the model can generate a diverse range of filter effects, as visualized in Figures C and D. These figures demonstrate the learned filter effects on samples from the 5K and PPR10K datasets, respectively. The neural implicit lookup table is trained using a prompt-guided optimization objective, which encourages the model to generate filter effects that align with user-provided prompts. This enables users to specify desired visual outcomes, such as increase contrast or warm up color temperature, and the model will generate the corresponding filter effects. The author's approach offers several advantages over traditional image enhancement methods, including flexibility, controllability, and interpretability. By learning a set of filter effects that can be composed to achieve desired visual outcomes, the model provides a high degree of flexibility and customizability. Additionally, the controllable attributes provide a clear and interpretable understanding of the image enhancement process. The experimental results demonstrate the effectiveness of the proposed approach, with the model generating high-quality filter effects that align with user-provided prompts. The authors also discuss potential limitations in future work, including the need for larger and more diverse datasets to further improve the model's performance. Here is the combined summary. The paper presents a prompt-guided image adaptive neural implicit lookup table approach for interpretable image enhancement. The approach involves predicting multiple parameters for image enhancement, including exposure, contrast, saturation, color temperature, and tint correction. Figures E and F demonstrate the sequential application of these predicted parameters on sample images from the 5K and PPR10K datasets, respectively. Notably, the sequential application is for visualization purposes only, and in practice, all effects are applied simultaneously. The predicted parameters are generated using a neural implicit lookup table, which is conditioned on the input image and a prompt specifying the desired enhancement. The lookup table is learned through a training process that involves minimizing a loss function comprising a reconstruction loss and a regularization term. The reconstruction loss measures the difference between the enhanced image and the ground truth, while the regularization term encourages the lookup table to produce interpretable and disentangled representations of the enhancement parameters. The approach enables flexible and controllable image enhancement, as the user can specify the desired level of enhancement for each parameter through the prompt. The neural implicit lookup table also allows for efficient inference, as it can be evaluated at multiple points in the input image to generate the enhanced output. The results in figures E and F demonstrate the effectiveness of the approach, with the enhanced images exhibiting improved exposure, contrast, and color quality compared to the input images. The approach also enables the generation of diverse enhanced images by modifying the prompt and the input image. However, the paper notes that the approach assumes a fixed set of enhancement parameters and may not generalize well to unseen parameters or datasets, highlighting the need for future work in this direction.